Hello and welcome everyone to the fourth in our Fault2SHA learning series. The point of this series is really to help all of those of us working in different disciplines relating to faults and seismic hazard assessment really understand what we're all doing and making sure that we're not sort of caught behind with certain topics that perhaps we didn't learn initially and just have to pick up as we go along, so that we can collaborate across disciplines and we can really understand the research talks and papers that we come across. Today, we're learning about Coulomb stress transfer, and who better than Ross Stein to speak to us on that topic. So I am absolutely delighted that he is with us today. In the spirit of our learning series, Ross is very happy for people to ask questions as we go along. So either ask a question aloud, or if you want to put one in the chat, I will try and collate them and interrupt Ross as we go along to make sure that your questions do get asked, because this is your chance to really try and make sure we understand the topic. If I give Ross a proper introduction that he deserves, we'd be here for an hour and we wouldn't get a chance to actually hear from him. So I'm not going to go on too much. I won't be able to do him justice. But for those of you who've come across Coulomb stress transfer, we've all cited Ross so many times, so we know who you are. He's co-founder and CEO of Temblor, an adjunct professor of geophysics at Stanford University, and a former senior scientist of the USGS. He's also given a TED Talk in 2012. So I like to think our Fault2SHA learning series is in good company there, with no delusions of grandeur that we're not as important. So with that, as I mentioned, we all cite you all the time. Your 84 publications, according to Scopus, have been cited over 11,000 times. So your influence is always so definitely inspiring us. So with that, I hand over to Ross. And as I mentioned, everyone, please do ask questions either directly or in the chat. Thank you again, Ross Stein.
Thank you, Joanna, for this opportunity to talk to people about something near and dear to my heart. And the message of this talk is that earthquakes converse by the transfer of stress. That's the argument I'm going to make to you and try to explain it in a way that everyone will understand. And I'm going to start right here with a Quakecaster to kind of reintroduce you to the ideas of earthquake occurrence. Why is that alarm gone off? Sorry about that. Okay, I think I've turned that off. All right, so what do we have in the earthquake machine? There are just 4 elements you need to create earthquakes. If you don't have any one of them, you never get earthquakes. If you have all 4, you only get earthquakes. So what are they? One is the steady motion of the plate's interiors, which are going to be represented by the cranking of this casting reel. That reel is attached by a high-tech non-stretch line to a rubber band. The rubber band represents the elasticity, the rubberiness of the Earth's crust itself. Then I have a couple of kitchen countertop samples sitting here on industrial non-skid, kind of this sandpaper-like surface. So we have a mass that's being pulled at a steady rate with a rubber band in there, and it's sitting on top of a frictional surface. So those are the only elements. So what I want you to do is just watch what happens as I crank as steadily as I can. Okay, so we sat there for several hundred years and then bang, we had an earthquake, right? So let me ask you some questions. Were all the earthquakes separated by the same amount of time? Shout it out.
No.
No. Okay, if we think of the size of the earthquake being related to how much it slips, were all the earthquakes the same size? Well, no. This is very bad news. If I can't make regular repeatable earthquakes with uniform non-skid sandpaper, kitchen countertop samples, and a simple rubber band, we're never going to get them in the Earth. So this is the most important bitter pill that seismologists have had to swallow in 40 years of research, which is that earthquakes are not regular and repeating. And this variability in the system is very, very powerful because it allows us to see much larger and smaller earthquakes, earthquakes separated by a lot of time and a little. When you think about it, if I am cranking steadily here, and if my rubber band is always within its elastic range, which it is, and since the mass has never changed in this system, what is the only explanation for this diversity of behavior? It's got to be the sandpaper. And what's amazing about that is if I feel it with my hand, it feels uniformly rough. It's very, very flat. It's not nearly as grungy as a fault is with bends and breaks and secondary fractures. And yet, that's the only explanation for this variability, friction. So one of the powerful insights of Coulomb stress triggering is that lowly friction rules the world. Friction is probably the most important variable in the system, and it's one that's extremely difficult to figure out. Yes, we can look at the central San Andreas where it's very, very straight and very isolated and say that is a smoother fault than, let's say, the faults that we would find in the central Apennines. But beyond that, it's very difficult for us to say anything about friction, except that it's got to be among the most important elements. Okay, let's ask another question. You saw what I could get when I had two bricks here. Now I'm going to take one brick off. Okay, so I've halved the load and I'm going to crank at the same speed. So I'm going to crank at a San Andreas 2 centimeters a year speed, same rubber band, same friction, but now half the mass. So now I want you to make a prediction. Am I going to get fewer earthquakes or more earthquakes? Am I going to get them closer together or farther apart? Okay, so I hope you took a bet. So if your intuition was that earthquakes would become more frequent, you were right, and that makes sense because the force, this is a force balance. The force resisting motion is the weight of the brick times the friction coefficient, something on the order of 0.7 or so. The force pulling on the brick is the length change times the spring stiffness. So I've halved the resistance, so it goes earlier, but I haven't stretched the spring as much because the resistance was less, so it goes for a shorter distance. So I think you saw that you indeed, with the same fault friction, with the same slip rate, with the same crustal elasticity, we can get earthquakes that are spread farther apart or closer together. And I think you also saw that even with a one bricker, I'm not getting regular repeating earthquakes. They're changing size. There's a variability there too. But we can see something very, very predictable about behavior. If for one reason or another, we can get a one bricker fault spot on a fault, we can get smaller earthquakes that are closer together in time. And I can go one step further. So now you can see, because it catches the light, this is the polished surface of the granite. This was supposed to be on the kitchen countertop, but on the bottom, we actually sandblasted it. So it's rough in a natural kind of way. So now what I'm going to do is simply turn this over. Now think about this. One side of this fault has perfectly smooth, low friction, almost Teflon-like conditions. But the other side, the sandpaper, is what it was before. So now what am I going to get? Am I going to get earthquakes? Is it going to purely creep? Or are we going to get big earthquakes? What's going to happen? So make your bet, and here we go. So you can see that it is kind of creeping, but not quite. There is still some kind of staccato pop, 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 pop occasionally, and it's not perfectly smooth, but we are getting more creep-like behavior. And again, San Andreas slip rate, same elasticity, same friction. And what's interesting about that is we obviously have places on the San Andreas, for example, that produce magnitude 8s. We have a place on the San Andreas that seems to produce 6 to 6.5, Parkfield, and we have a place, the creeping section, that produces not only creep, but more earthquakes than anywhere else on the San Andreas, except that they're very small. All of that, and that creeping section is one in which on one side we have a perfectly smooth fault because we have clay, and on the other side we have a rough surface, granite. So this huge diversity of behavior we can easily reproduce in this simple kind of way. Now, you might say, but wait a minute, earthquakes don't occur along a 1,000-kilometer fault in isolation. What about the interaction of one earthquake rupture site to another? And that's a really good question. So to answer that, what I'm going to do is put some sections on in series. Okay, now again, the question to you is, who's going first? Is it this guy, or this guy? You might think it's this guy. Who's going second? Well, could be this guy again, could be this guy. Who's going third, etc. Now, this may seem like an easy question, but I promise you it's a trick question. So here we go. So it gets very interesting very fast, right? This guy went first, but he also went second and third because he had to load up his sister. And sometimes she would go and sometimes this guy would go, but sometimes when the spring tension was tight in both, they would all go together. And this is exactly what we see in the Earth. And this is what makes earthquake prediction such a ridiculously hard problem. It's that no little earthquake knows it's marked for future greatness. It doesn't know if it's going to bring its siblings along with it. And in general, it doesn't. So we can look at the Lander site. 3 faults barely connected that on a good day could produce a 6.5, but they got together in 1992 and produced a 7.3 when they all went together within tens of seconds. This section, 6 section went together. But we know from paleoseismology, that's not typical. Mostly we get those independent events. And so since we don't know what the state of friction is or tension is between these, it's very, very difficult for us to make any kind of forecasts about that. But it's an essential part of the problem we're trying to solve. Now, I want to show you one more thing, and maybe it's the most important. Okay, I'm going to get this guy kind of tensioned up again. Okay, what's going to happen if I lift the top brick? It's going to go, right? Yeah. Why did it go? Because it was loaded and I unclamped the fault, okay? I reduced that force. If we think of a strike-slip fault, that would be just reducing the force that keeps the two faces against each other, which is related to the weight of the rock above them. So if a fault is close to failure and I unclamp it, I can trigger failure, okay? What else? If it's close to failure and I pull on the spring just a little bit, again, I can trigger an earthquake by increasing the shear stress. Now, what's important about this is this only works if the fault's close to failure. If the fault isn't close to failure, lifting a brick does nothing, pull on the spring does nothing. This is the Coulomb criteria, that by unclamping a fault or increasing the shear stress, or both, I trigger failure. And by the same token, if I can put another brick on, if I can clamp it further, I will inhibit it from failure. And if I pull the spring the other direction, I can inhibit it from failure. So faults can be brought closer to failure by transferring Coulomb stress, or farther from failure. Closer to failure, we call it stress triggering. Farther from failure, we call it stress shadowing. So those are the two phenomena, and it only works if faults are close to failure. So in the arguments that I'm going to now move to in the slides, you'll see that it generally does work. And the implication of that is that most faults spend most of their lifetime very close to failure. It's the only explanation for why Coulomb stress triggering would work. And it's an interesting thought. Only close to the very biggest faults do we ever significantly drop the stress. The rest of the faults are all just about ready to go at all times. And there's no other explanation than that. So that is the concept. And what we're going to do now with the slides is just go from this one-dimensional world to a more three-dimensional world, show you some examples of how this works, and show you what's missing from this view of the world that seems to control earthquake occurrence. Okay, so now I'm going to share my screen. Okay. And Joanna, we're just seeing what we should be, right?
You're still seeing the bottom slides.
We're seeing the bottom slides.
Now we're good.
How is it? Now it's good. Okay. So this is what we look at, but now what we're going to do is we're just looking down on a map at a strike slip fault, and we're seeing that the shear stress increases beyond the tips of the faults, as you kind of would intuitively expect. Okay, so that is red is where we're further bringing the faults close to failure. Okay, what about unclamping? So these lobes, which look quite a bit like the kind of traditional compression and tensional lobes, are where we're unclamping the fault. And we multiply this unclamping times the friction coefficient. Let's just think about 0.6 or 0.7 or something. And we put those two together and we have the Coulomb stress. And what's interesting about it is it's got these areas, the kind of blowtorch zones beyond the tip, but it also has these side lobes too, where the effect of this unclamping is more profound. I don't know why that keeps disappearing. Okay, this example is one in which we're assuming that all the faults that receive stress, we call them receiver faults, are parallel to the slipped fault. But there are other assumptions we could make. We could resolve the stress on mapped faults or extensions of mapped faults, where we imagine faults to be rectangles of various orientation. We could resolve stress on what we call optimally oriented faults. Those are the faults on which the Coulomb stress is highest at any point. That's often used. And then there's a third possibility, which is we resolve stress on focal mechanisms themselves, beach balls. There we have the yin-yang problem that we don't know which of the two nodal planes is in fact the fault plane. But the benefit of focal mechanisms is we really do know that there's a fault there with that orientation. Okay, so now let's try this out on that Landers earthquake that I was referring to before. So here's the Landers earthquake that was kind of an overachiever and gave us the 7.3. And here, retrospectively, is the stress pattern produced by the earthquake. So we see the big lobe of red beyond this end. The other lobe, it's broken up because there was another little earthquake, the Homestead down here, Joshua Tree beforehand. And then we have the side lobes, this big one and this little one. Well, first of all, why aren't the side lobes equal in intensity, like I showed you in the original example? That's because basically the side lobes feel the ends of the fault, and this fault is kind of bowed. So this one gets big because it's closer to the ends. This one gets smaller because it's farther than the ends. And here are the earthquakes that occurred in the first 3 hours after the Landers event. So most of them are along the fault. And this is, by the way, optimally oriented Coulomb stress change receivers. But we see some early aftershocks in this zone, a few up here, one out here. Okay, what happens 3 hours, 8 minutes later is we have a magnitude 6.5 here. Now things start to get interesting. Is that a separate earthquake or is that an aftershock? From a Coulomb standpoint, it's a contingent event. It's an event that happened there because stress was raised off the fault. But you might say, and you should be a skeptical audience here and say, well, look, I could throw a dart at this map and I might have a very good chance of hitting some red. So prove to me that this isn't just happenstance. And we can, because there were 10,000 aftershocks that occurred here. And you can see that the vast majority of them occur in the red zones, including a 7.1 that occurred 7 years later. So this tells us that these effects have some staying power. And it tells us that these stress trigger zones do seem to be the site for subsequent earthquakes. But a skeptical audience member would still say, but wait a minute, I do see some earthquakes in the shadows, in the stress shadows. Doesn't that falsify your whole point of view? And we would say, no, that the Coulomb hypothesis is not that there are no earthquakes in the stress shadows, but that in the stress shadows, the rate of earthquakes drops from what it was before. So that's a subtle but important difference. Okay, and so as a result of this, we produce software that's available. It's MATLAB software so that anybody can make these same kind of calculations. Now, what the message is that these stress changes are permanent, but the effect on seismicity is not. It fades with time, just as aftershocks do. And so, what about the bigger picture for a longer time period? So if we pull back now in Southern California, we see something else interesting. So here's the Landers earthquake we just looked at, and I mentioned that it produced or seems to have influenced the occurrence of a magnitude 7 7 years later. But we also have the Kern County magnitude 7.3 in 1952 and the Owens Valley earthquake, perhaps the second largest earthquake ever recorded historically in California. And interestingly, trigger lobes of all three earthquakes seem to meet at the site of the 2019 Ridgecrest events, a magnitude 6.4 and 7.1. So that's interesting. But again, you might say, well, there's about a 5% chance that if you hit this thing at random with a dart, you could get a redder zone than this. So there's still some chance that this is just happenstance. But then something interesting happens. If you superimpose earthquakes of magnitude 4 for the last century, you see that most of those earthquakes are occurring in the red zones. Not all, but most. And that's remarkable that earthquakes over this 100+ year period could be controlling the entire seismicity pattern for Southern California. So the greater LA area seems to be a zone in which these two lobes interact. These two lobes, there again are places that violate this expectation, but by and large, it's very consistent. And that says we need to understand how these stress changes translate into seismicity changes and how long they last. So let's look at that. And the way we're going to do that is with the Dietrich seismicity rate equation. Dietrich 1994 is probably one of the most important papers of the last century. And what is it? Let me show you what it means. So imagine you're on a fault. It's just ruptured here. You're out here in a region that has had a 1 bar stress increase transferred to it. And this is, let's say, the San Andreas. It has a stressing rate of about 0.1. Maybe the San Andreas is 0.2 bars per year. And then you have this sudden stress increase. So what does the Dietrich equation predict that this is going to produce? It's going to produce something like this. So it's an impulse and then response and decay, looking just like an aftershock decay. So that's what is expected. It's not a permanent increase in seismicity. It fades, and eventually it'll go back to where it was or almost where it was before. So the first message of the seismicity rate equation is that the response of a fault to a sudden stress change is a dramatic increase in seismicity rate that decays. The second important message is that what these stress changes do are amplifying seismicity rate changes, seismicity rate, excuse me. So in other words, if the seismicity rate is 0, then you're not going to get any effect from a Coulomb stress change. If the background seismicity rate is very, very high, you're going to get a very, very strong effect. The next message is that it depends on the stressing rate of the fault. Now we're looking at kind of like the Japan Trench, a very high stressing rate. We still put a 1 bar out here, but look what happens to the response. It's much shorter. What's the message about from this? It's that you might expect aftershock duration on the Japan Trench to last a year or 2, on the San Andreas a decade, and in New Madrid a couple hundred years. Seismicity, aftershock durations are a function of stressing rate. The slower a fault is stressed, the longer the aftershock last and the longer these stress effects last. So that's a really interesting idea. Of course, it's a theory. It's not necessarily correct, but many, many efforts to test this theory have been propounded, and in general, it's found to work very, very well. Okay, with that in mind, let's go back to Southern California and say, let's put those concepts to work. And here is what we get when we apply Dietrich's equations to the stress changes that you just saw. So now we don't have blue zones, stress shadows, and red zones. We just have various hues of red. Here are the stress shadows, where we don't predict any earthquakes at all. There are some. And the reddest zones are where we predict the most earthquakes. So now what's entering the picture is not just a stress change, but the background seismicity rate. And so it's interesting that notice that there are a lot of earthquakes here. This was all a big red lobe, but this one is much lower and this one is much lower because this had a higher background seismicity. So the blotchiness of real patterns of seismicity are better explained now than before. There are areas where things really turn on and areas where they don't. Now, for most of my professional career, David Jackson has been my nemesis star. Everywhere I go and present an idea, David is shooting it down. And at some point over the last 30 years, finally, I came to the conclusion that in all of our battles and scientific arguments that we have had, he's been mostly right and I've been mostly wrong. So I changed tack and started working with David. And that's been a real gift in my research career. But one of David's strongest points is that only prospective testing counts. What I've shown you so far are retrospective efforts. And David says you can always cook the books, intentionally or not. And therefore, in science, what matters is predictions. Now, that's hard for anybody who's studying earthquakes or paleoseismology, because it's very hard to wait around for that next earthquake occur. But here we do have the chance to make short-term predictions, publish them or submit them, and see how they do. So this is an area that we published with a prediction. And we published it in 2005. It was a 10-year forecast for magnitude 5 and greater. So how'd we do with a Jacksonian viewpoint? Here's the forecast for where we said earthquakes were most likely to be. In the entire box, we're predicting a 92% of a 5 in that 10 years. And in these reddish zones are where we thought it would be highest. Here's what actually occurred. Yes, we did have a magnitude 5 or larger earthquake in the box. We did have more earthquakes over in this zone, but not quite where we expected them to be. And this one is not at all where we expected it to be most likely. And we can also look at smaller earthquakes just to get a better gauge about what we did right and wrong and compare that with our forecast. We did pretty well over here. We did decently here. We really missed the fact that the Hector mine aftershocks would be more abundant and last longer than we predicted. So I would think it's fair to say we did okay. All right, here's another forecast we did 3 years later. And that's in the area around Wenchang, China. So you remember this horrible earthquake, a magnitude 7.9, that occurred in 2008. Here's basically a decade of background seismicity smooth. So if that earthquake hadn't occurred, that would be our forecast for the future. All right. Now we introduce the magnitude 7.9 earthquake and add its stress contribution, and then calculate what we would expect for magnitude sixes. And that's shown on this side. And some things should look familiar to you. So this white zone here and white zone there, those are the stress shadows. So compared to what they were before, this is much wider now than it was then. And then beyond the ends, and this is a thrust earthquake, doesn't quite look the way we've been seeing things. These guys are much redder, and this is much redder than what we see here. And those are the trigger zones. Okay, so how'd we do? Well, this time we did much better, right? We have 2 earthquakes in among the reddest zones, and we have no earthquakes in the stress shadows. So again, that's a blind forecast. It's published. There was nothing we can do to cook the books, so we kind of satisfy David's concerns. Here's another one on a much shorter time scale. There was a magnitude 6 earthquake in Kumamoto, Japan in April of 2016, and my close collaborator Shinji Toda, who's contributed to just about everything you're seeing here, made a quick Coulomb calculation and was interviewed by the press, and they published his map shown here for this earthquake. And what Shinji was pointing out was that the Futagawa fault here, a major fault, was in a stress trigger lobe, as was the Hunagu fault here. And he said larger earthquakes could occur on either one of those faults. Well, the next day, both of those faults ruptured, producing a magnitude 7.0 earthquake. So there is another very rapid blind test. And you can see that that magnitude 7 earthquake is also broadly consistent with the trigger zones and the shadow zones. So I think what you've seen so far is we can go beyond just the static Coulomb stress. We can apply the seismicity rate equation of Dietrich, and then we can begin to do more direct forecasts, probabilistic forecasts of earthquakes. But let's take a little closer look at the stress shadows, because they're really interesting too, and they're the good news part of earthquake interaction, that earthquakes can be inhibited on faults, not just promoted. So here is a case we looked at on the San Andreas. So in 1983, we had a magnitude 6.7 here and a 6.2 here. And we're calculating the stresses that they impart to the San Andreas. So this is one of those cases where the receiver fault is just a simple straight line here, and we're only looking at the shear stress on the fault. In other words, put another way, we're assuming that the friction is 0. And what you can see is that these 2 creep meter sites are in the center of the stress shadow lobe. This one is just on the edge of the trigger zone. Those are the only creep meters on the fault in this area. Sorry about that. Okay, and look what happened. In this zone that gets hit by a stress shadow, the creep meter goes backwards, and it goes backwards for several years. And down here, it goes backwards for a little longer. And up here, it goes forwards. So roughly speaking, we can see, because the San Andreas seems to have very low friction, it responds very quickly and fully to these small changes in stress. This is just, less than a half a bar of stress. And by the way, if I just put my hands like this, and I push as hard as I can with the base of my palms in contact with my palms at 45 degrees, I'm putting almost a bar of Coulomb stress across my palms. So these are very small stress changes, and incredibly, they seem to be large enough to cause the San Andreas to go backwards. Here's another case of the impact of a stress shadow. These are the as best we can measure, these are the earthquakes in the San Francisco Bay Area in the 75 years before the 1906 earthquake. That's from the start of the gold rush until the 1906 event. And here are the earthquakes in the 75 years afterwards. So it's almost completely shut down. Earthquake rate is probably a tenth of what it was before. And that is at least justifiably explained by all of these subparallel faults in the Bay Area being in the stress shadow of the 1906 earthquake. Its trigger zones are way down here to the south and way up out of this slide to the north. And this is something first promoted and explained by Ruth Harris and Bob Simpson, and then later studied by Tom Parsons and also by Fred Politz. So it's an interesting, perhaps very important case for society that the San Francisco Bay Area blossomed in terms of population during this very unique period of seismic sleep brought on by the 1906 earthquake that is in no way typical. Okay, now, if you wanted to be skeptical and critical, you might say, but Ross, aren't you grossly oversimplifying the crust and the behavior of faults? And that was a point brought home to me by my mentor, Bob Wallace, the father of paleoseismology, who gently remonstrated me by giving me this drawing in about 1986 or so. And he said, no, what you're doing on the left has nothing to do with actually how the Earth looked. This is what it looks like. And I had him sign it because I thought this was a beautiful moment. And I've often thought, well, okay, H2O, and there's a lot of things that we are oversimplifying. Two comments about that. First, the fact that we can typically explain maybe 2/3 of the earthquakes in this ridiculously oversimplified way is good news. But it's also, he's right. We've oversimplified things too much. And so in an effort to try to respond to that, we've made recently a modification to how we typically go about doing Coulomb stress transfer. And that is, we're using focal mechanisms as our receiver faults rather than map faults or optimally oriented faults. So here's a case. This is the magnitude 7.8 Kaikoura earthquake. These are focal mechanisms. And if the focal mechanism has been brought closer to failure, it's red. If it's brought farther from failure, it's blue. And so you can see that in real life, faults are much more complicated, as Bob Wallace pointed out, than simple map faults. And the simple map faults are rather kind of parallel. They're strike slip with some thrust component. But if you look in detail here, they're all over the map. So now we've captured that. We've let focal mechanisms tell us at that point, at that location, that's what's really there. And here's what I want you to see. On the right is a map of seismicity rate change. We're comparing the year after the Kaikoura earthquake to the decade beforehand. And it's obviously red in here. We've seen mostly red mechanisms in here. But what I want you to see is, see this blue out here? Well, these mechanisms are blue. And see, it's red up here. These mechanisms are red. We get some yellow here, and we get some red, yellow here. We can go down here, and we see the red extends way down to the south, and we're seeing that in the data. Christchurch is turning blue. We're seeing that. So that tells us that maybe focal mechanisms are a better way to try to calculate this. Now, there's a cost. One cost is you need to have a good focal mechanism catalog, and that doesn't exist everywhere. The other cost is that you don't know which of the two nodal planes is actually the fault plane. So we take the most positively stressed plane in these maps. That means if it's blue, it really is blue. It can only be a stress decrease here, and that's when we see it correspond to a seismicity rate decrease. It gives us confidence. And I want to point out that the first people to present Coulomb stress triggering analysis on focal mechanisms was Jean Hardebeck and her co-authors Julie Nazareth and Egil Haukson. So that was really a crucial and important paper, and we've just drafted on that. and develop more tools. And the Coulomb software has tools to deal with focal mechanisms. So all of that is built in. So what are we doing now? And this is something that Tembler is doing, is we use focal mechanisms, we use the seismicity rate equation that you saw, and we use the stress transfer from all the earthquakes that are large enough that we really know what their sources are. So now I want to show you a forecast we've made for Japan. So starting on the right, we're using the global earthquake activity rate model, which is a time-independent model, not a Coulomb model. And you can see that the two recent earthquakes, the February and March event, are broadly consistent with that, in the sense that a higher rate of magnitude 7 to 7.9 earthquakes were expected there compared to the Nankai Trough or other sites. Now, what we do in the Coulomb model is we consider all the stress interactions. And now you can see it's much more gloppier. It's much more concentrated into lumps. And here where these two earthquakes occur. And here is the region of the Tohoku earthquake, which is white because its stress has been transferred to this kind of halo around it. So in Jacksonian terms, since we gave this to our clients in January and these events occurred in February and March, it's a blind test. You know, you can't ever be too conclusive about two earthquakes, but these are suggesting that we can do a lot better than time-independent models, even good time-independent models, by applying these tools. Okay, so we've
sorry, we just had a question asking if you could clarify the colors for the beach balls and how you decide what colors to use on your beach balls.
Okay, great question. Let's go back. Okay, so you can see the scale bar down here. Here we're coloring them by plus or minus 0.1 bars. There's nothing magic about 0.1 bars, but in a lot of studies, what we see is that if you stress a fault by 0.1 bars or more, you begin to see changes in its seismicity rate. So it's not a threshold, but it's a point at which research suggests this matters. But this also means it's saturated. There are stress changes close to the Kaikoura source that are 100 bars, and you're not really seeing that. But what we're interested in seeing is this broad pattern out several fault lengths away. So when we get down here, out here, we're really getting to be very, very small stresses, about a 0.01 bar. So you can see now how they're colored, and you can also see the great range in focal mechanisms. These things are not simple and parallel to each other. So we're never going to get it right with mapped faults. That's the problem. Okay, so at this point, all of my arguments have been about static stress triggering. And that's how I believed the Earth worked, even though there was a lot of research on dynamic triggering, the stresses carried by the seismic waves, but they looked really inadequate to me. And then I got a piece of calligraphy from my mom. And this is what she sent me. And they seems like pretty good watchwords, especially when it comes from your mom. And what it really meant is I was about to be shown how wrong I was. So here it is. In 2012, the largest strike-slip earthquake ever recorded, maybe by a factor of 10, occurred in the Indian Ocean. It looks like a traffic accident, not a typical strike-slip earthquake. This is nobody's idea of a magnitude 8.6 strike-slip earthquake, but there it is. And immediately, earthquakes started to occur around the world. And I looked at those, and I looked at the preceding rate and decided, this is just a mirage. These aren't really global aftershocks. And here's kind of where they occurred. These are the 5.5s and larger. And okay, are these just typical earthquakes or are they global aftershocks? And the first thing you notice is they're not close. They're not concentrated or decaying away from the epicenter. So that doesn't make them feel like aftershocks. And they're occurring there where the normal earthquakes are, typically around the Pacific Rim. So in that sense, they don't look unusual. So I concluded they were a mirage, and Fred Politz, my colleague in my office, said they had to be aftershocks. So I said, oh, Fred, you've got to be wrong. And then Fred showed me this figure. So what is this figure? We're looking at a couple of weeks, the 10 days before this event and the 10 days afterwards. The rate of worldwide magnitude 5.5 was about a half a day until the moment of this event, and it shot up to 5.5 and decayed over something like 2 days to a week. And further, this is the average. The red line is the average in the week or the 10 days beforehand. The black is the 20-year average with its confidence. And the green is if we just look at the 2 days after large earthquakes around the globe. So anything above the green is highly significant, and probably everything above the gray is significant too. So clearly I was wrong. And by the way, we've removed any earthquake within 1,500 kilometers of the main shock that you and I would call its static aftershock. So we're truly only looking at global events. So this is astonishing. So you probably saw in the corner of my studio here, my inflatable globe. And since, as you can imagine, I have a lot of rubber bands, and because I'm a very sophisticated scientist, I have a lot of sticky dots. So I started putting those earthquakes on that globe, and I got some big rubber bands and discovered I could pretty much fit the location of all these earthquakes by rubber bands that just form a 90 degrees to the main shock. And I got, this is like, you can see, it's about a 3-foot wide globe. And I ran into Fred's office with my globe and said, you know what, they have this pattern. And Fred went back to his office and he did this. So this is a spherical harmonic dynamic model that he built. And it's the peak dynamic stress. And he's done this in a very clever way. He's not looking at the maximum stress, which obviously is higher, closer to the main shock, the star. He's looking for the duration of that signal above a threshold. And when he does it that way, then you get this signal here, and you get the large signal at the antipode too. Okay, so I ask you, who's better? My middle school version of science or Fred's obviously show-offy version? We won't let you vote yet. So first of all, the message here is that what you consider to be your judgment and wisdom can be pure bias. I was biased against seeing this dynamic effect because it went against what I thought to be true. And so I was very fortunate that I had such a good colleague who didn't suffer from my own biases. Now, these are love waves, and love waves are much more strongly produced by strike slip earthquakes than thrust events, and they tend to promote failure on vertical strike slip faults because they do this. That's their motion. So Fred then looked at love waves from the biggest earthquake that has been well recorded, the 9.2 Sumatra event, and compared that to this earthquake, which is only 1/10 of the size. And look at this, the love waves of the Indian Ocean earthquake are all larger than this much bigger event. And if you're not familiar, L1 is the direct route, L2 is the indirect route, and it'll keep ringing over and over again. So these waves really do matter. And if there is a smoking gun, it's going to be what I'm showing you next. If you look at the cumulative number of percentage of strike slip earthquakes around the world, normally about 1/4 of the world's earthquakes are strike slip, half are thrust, and the rest are normal. And look at what happened in these few days after this event. Nearly 65% of the world's earthquakes right after that event were strike slip. It's very, very unusual. And it decayed quite a bit like an Amori decay. So in that sense, these have to be globally distributed up to magnitude 7 aftershocks, triggered by stress, but not static stress, the stress carried by the seismic waves. So if you throw a rock into a pond, those ripples that go out, you can imagine the amplitude get lower and lower, but the duration gets longer and longer. Duration probably matters because if what you do to a fault is you do this, the net effect is that not that the fault gets pushed toward failure. But if you do this for a long period of time, in other words, 100, 200 seconds, maybe that's what triggers failure. So where does this leave us? My view is that most earthquakes converse by the transfer of static stress, but some extremely large, extremely rare earthquakes are able to trigger failure on what we might call overripe faults. And I put up this picture of the rowing shell, not just because my collaborators and I are moving backwards, kind of blind, but also because you're seeing this beautiful complex interaction of waves. The bow wave of the boat, the waves formed by the dipping of the paddles, and you can see how magnificently complex the production of stress waves are in the earth. So our ability to understand that part of the problem is very limited, but it's a fascinating door that we can go through. And so now I would just like to acknowledge my fantastic collaborators, Shinji Toda, Volkan Sebelgan, Jin Lin, Kelsey Linton built QuakeCaster. We have a USGS open file report and several papers on building it and teaching with it. Of course, Fred Politz, who kept me from being blindsided, and Jeremy Shar, who built what we call fishnet stocking stress, which is another add-on to QuakeCaster, which I haven't had time to show you. So with that, I would like to just leave you with something else about moms that I ran into when I was at New Orleans for the fall AGU. Thank you.
Ross, thank you. While you were talking, a couple of questions did come up. So I thought if I ask those first, and then if people have more questions, they can post them or ask them directly themselves. So one was asking you to comment on the influence of distance earthquakes on decreasing seismicity rate.
Distant earthquakes, you mean other remote earthquakes?
I assume so.
Okay, what can we say? In general, the static effects are important over distances of about, 2 or so fault lengths away from a main shock. So in a kind of a broad sense, if we look at a situation like this, and if we think of the black line being the rupture dimension, if we go twice as far in all directions, that's its sphere of influence in a static effect. In the sense that all earthquakes have roughly the same stress drop, that would be true no matter how big it is. If it's a little guy, if it's a little 6, then 30 or 40 kilometers is the distance over which it's affecting its neighbors. If it's a magnitude 8, then it's maybe 300 kilometers. When it comes to dynamic stress, this is much less clear. We have a few cases where there really are other smoking guns. Here's the reason why dynamic triggering is so complicated. If, when the seismic waves arrived, that earthquake was produced, it would be simple. And we see that, but we see that very, very rarely. Almost always in these dynamic cases, like the Indian Ocean earthquake I showed you, these global aftershocks are not instantaneous. They take days, maybe up to a week to occur. Why? That isn't clear. It isn't clear what's going on before they occur. And because of that, it's very, very hard to build this into a forecast tool. There's just too much we don't understand.
Thank you. There's quite a specific question looking at your 10-year prediction experiment from Japan. And it says, what was the setup of receiver fault geometries as they were quite different over the large region. For example, the 2017, and apologies for my pronunciation, Zhangjiakou earthquake was a strike slip event, while the 2013 Lushan earthquake was a thrust fault. Both were in the very red zones after the 2008 Wenchuan earthquake.
Okay, great question. So what we're doing here is using beach balls. And why is it that seismologists are attracted like moths to a light to Japan? It's because of the data. And it's because of the very, very high slip rate. So we have a magnificent focal mechanism catalog from JMA for Japan. And we have fault slip rates basically 3 times higher than what we have in California, for example. So it's an embarrassment of riches. And so here, the focal mechanisms that we're seeing in Kyushu are generally, I don't have a map here to show you those mechanisms, but they're generally strike slip. Here, they're generally thrust. One of these earthquakes is in slab, high angle reverse. One is a megathrust event, low angle reverse. And in inland Japan, we are seeing a combination of strike slip and thrust events. So we're basically trying to use what we think are the active faults. And we are adding the stress contributed by all large earthquakes since 2011. And for the background seismicity, because remember, stress changes amplify that background seismicity in trigger zones or suppress it in shadow zones, we're using the previous decade of earthquakes. In other words, the decade before the Tohoku earthquake.
Thank you, Ross. There's a question here now about how do these stress shadows and loadings evolve on a long, i.e. many seismic cycle timescale along a big fault, so such as the San Andreas fault? Are there certain areas that are more often positively or negatively loaded than others? And can you see that? For example, they said in the topography.
So that's an interesting question. And obviously, faults aren't straight. They're bends and breaks. And at those bends and breaks, you will build up stress off the fault. And in a famous paper by Jeff King, also one of my wonderful collaborators from times past, Jeff showed that when you have a bend, you have to do off-fault damage and off-fault deformation. You can't conserve things through the bend. And so in places like the Bay Area where we have offsets or jogs, we have an offset here that's dilational, and we seem to have a basin formed, the San Pablo Bay. Other places where we have different kinds of bends, we have raised topography formed. I mean, the entire Santa Cruz Mountains here is caused by a bend in the San Andreas, a bend of about 10 degrees or so. So these stresses contribute to permanent deformation, but the Coulomb stresses in terms of their ability to cause subsequent earthquakes in those regions probably fades. If you look at a seismicity map for, let's say, Western Turkey, what's interesting is you generally don't see a lot of earthquakes on the major faults. You tend to see a lot of earthquakes at the bends and breaks and junctions of faults. And that's telling us that these places spend their time working out the stresses that are imposed by big earthquakes, that they are constantly producing little earthquakes because they have to make the adjustments.
Thank you. I'm conscious we're slightly short of time, so I'm just going to do the 2 last questions. So sorry for those of you who didn't get your questions asked. But one is about how most of the examples shown were for areas with very high strain rates, such as plate boundaries. Are you able to comment on these ideas for low strain rate regions? And are the ideas universal in your view? And then the next question, I'm just putting these together for you, was that you showed that the earthquake and earthquake cycle are controlled by the friction of the fault and the normal stress on the fault. In a real fault system, is it possible for us to identify these 2 values, and how can you actually use them?
Okay, so one of the problems with this analysis is we're not measuring stresses at all. We are simply modeling stresses. So it's a fundamental weakness of the method, that if we could measure this, if we could measure the stress on the rubber band, we'd be doing a much better job. And instead, what we can do is measure the stretching of the rubber band at the surface through GPS. So we are never able to actually measure stresses in faults. You know, with rare exceptions, almost no stress measurements are made at any depth at which earthquakes occur. So it's a fundamental weakness, is that, and that's why what Bob Wallace was arguing was very, very good, is that, you know, you're oversimplifying the earth and you're calculating stress. Our comeback would be, it seems to work. But is that a strong argument? I don't know. Okay, so now the final question, what about plate interiors? And I did mention that one of the huge implications of the seismicity rate equation is that in plate interiors, aftershocks should last very, very long, and they do. And so today, for example, the USGS assumes that the high rate of seismicity in New Madrid means that it has a high background rate and is more likely to produce another local earthquake there. But if Seth Stein is right, and the arguments that Shinji Toto and I have made are right, instead, those are simply long-lived aftershocks of an earthquake that occurred 200 years ago. And they're not telling us that the background rate is high at all. It's probably the last place we're going to get the next earthquake. It's blown its wad. And so this is a fundamental difference of view. It's a view kind of illuminated by the seismicity rate equation. And it's very difficult to know who's right. You know, another example would be Australia. How are probabilistic seismic hazard maps made for Australia? Well, they just take microseismicity, they smooth it, and they scale it up. And they say, okay, that's it. But the problem in Australia is no mapped active fault has ever been associated with a large earthquake. And it's possible that that map of microseismicity is really a map of the aftershocks of prehistoric earthquakes. And it's giving you exactly opposite to what you want, that the areas with those earthquakes are the last places you're going to get the next one. So this is an unsolved major problem. And Coulomb has something to say on this problem. And is all I think I can say confidently is we are not doing it right.
Thank you. Well, it's good to know that even you are saying that we can't do everything right at this point, Russ. Thank you so much. There's been a lot of messages as well, just saying thank you in the chat and really appreciating your lecture. And I think we've all come away with a better fundamental understanding of Coulomb stress transfer, particularly when it works and also the limitations than we did an hour ago. I have a couple of quick Fault2SHA announcements. Our next session in the Fault2SHA learning series will be on Monday, the 10th of May by Laura Perizza, and she's going to be talking about false friends in seismic hazard assessment. So what are those terms that we all use in different ways and cause confusion, and hopefully provide some clarity on that for us. Another announcement is that the Fault2SHA have a session at ESC, which is on the 19th to 24th of September. That's imaging and modeling 3D fault complexities in Fault2SHA. And the deadline for abstracts is on April the 19th, so just 1 week away. So please do submit to that if any of you would like to take part in that session. With that, as I say, thank you everybody for joining, and particularly to Ross for presenting. We've really enjoyed it, and see you all again at our next event. Hopefully in person at some point.
I'm looking forward to hearing Laura.
Great. Thank you. Thank you, everyone.
Bye.